Welcome back to General Chemistry. Let's talk a little bit about phase diagrams and how we can look at solids. Remember that when we have a molecule, let's say this is a molecule here, and the molecule is polar, then if you have another molecule of the same characteristic that is going to be polar as well, the polarity of these two will interact and it will make some kind of let's call it bonding for lack of a better word. So, but it's not really a true chemical bond. It's just the interaction that allows them, these two molecules to stick together and so on. And of course, we have said that you may have many different kinds of bonding depending on what kind of molecule it is. One that is interesting to talk about is when you have a hydrogen atom that is connected to something that is very electronegative, therefore it's going to be pulling all the electrons towards this side of the molecule, allowing this hydrogen to be kind of only a proton. And if you have another molecule similar to this over here, then the excess electrons of this on this side is going to make this molecule more electronegative, and therefore there's going to be an attraction, pretty strong attraction between the hydrogen and this thing. And this is what we call hydrogen bonding. So you have cases like with oxygen and hydrogen, nitrogen and hydrogen, fluorine and hydrogen, that the electrons are really pulled to the side of the more electronegative atom here, and then the hydrogen, there are no more electrons there, so it just becomes a proton there, and this proton then, as it is exposed, is going to act very strongly. And that's the kind of hydrogen bonding that we were talking about. We call it bonding because we don't have a better word, but it's not truly a chemical bond. And this is a good example here. The hydrogen is highly attracted to the oxygen here, or here the hydrogen attracted to the oxygen here. And you can see that this strong attraction makes a difference in the properties of these elements. So for instance, let's say that I have ethanol and dimethyl ether here. They both have the same formula. They have 2 carbons and 6 hydrogen, 1 oxygen. But in one case, in the case of the alcohol here, the ethanol has the oxygen at the end. So the molecule here would have the 2 carbons connected, and then you have one of the carbons connected to the oxygen, and the oxygen is going to be connected to the hydrogen. While in the ether case, the oxygen is between 2 carbons. So this would allow these 2 molecules, even though they have the same chemical formula, to have different properties. And one of the properties that we can look here, you see they have the same mass, but one of the differences we can see here is the boiling point and the melting point. The boiling point, for instance, of the ethanol is much higher, 78 degrees versus minus 22 degrees for the ether. And this is because the connection, the bonding between the hydrogen and the oxygen of another molecule. And very similar would be for the melting point. So the melting point, you can see here, is minus 114, and in this case is minus 138. So this is how the way that the molecules behave based on their structure is making sense. In general, you can always think that the substance, as Matt said, can have any of the 3 major phases. It could be a gas, it could be a liquid, or it could be a solid. And it's going to be a change between the solid and the liquid at a particular temperature. It's going to be a change between the liquid and the gas at a particular temperature. But the interesting thing here is that all of this depends on the pressure. If I am at 1 atmosphere pressure, which is most of the time, then I can increase my temperature and go along this side. The solid will heat up until it cannot heat anymore, and then it will become a liquid. There is a moment here, remember that the temperature is not going to change because all the energy that we put into the system is going to be used by the solid to convert into a liquid. Once I have all my liquid, then the liquid will start to warm up until I reach this point here, which is the evaporation point. And then again, I'm going to stay here for a little while. The temperature is not going to change until all my liquid is converted into a gas. Once I have all converted into a gas, then my gas will increase the temperature going in this direction, right? Now, if I increase the pressure, the temperature at which the liquid is going to be becoming gas increases. And I can do this until I get to this what we call a critical point, where there is no connection, there is no distinction really between a very fast liquid and a very slow gas. They look very similar here. So anyways, look at this. Let me get rid of these lines here. Let's have a look. In the case of water, we have a very interesting phenomenon here. Have a look at how the difference between the solid and the liquid here goes kind of backwards as we increase the pressure. Goes like this. Okay. So what happens, for instance, if I have a solid here, and let's say I am at atmospheric pressure, and then I step on it, like if I am using let's say that I am using my ice skates. So I will get to a higher pressure here. Then the ice is going to convert into liquid. So what happens here when somebody's skating is that you are actually on the surface of a liquid. And that's what makes it to be so fast. There is hardly any friction and so on. It's a very interesting thing here, and I will mention other examples in class. Anyways, so in general, when you look at solids, we can talk about solids in many different ways. You can have crystalline solids, or you can have non-crystalline crystalline solids where they are amorphous, they don't have really a shape. And then it depends on if you're talking about the kind of solid that is based on just on the molecular shape of the molecule. You can have ionic solids, like in the case of sodium chloride, or you can have other kinds of solids based on just the atomic composition, like in the case of metals and so on. This would be one kind here, the metallic metallic bonding into some kind of solid there and so on. So let's talk about how we work with these solids here. One thing we can do is analyze the solid by looking at it, and of course one way of looking at it would be by the use of X-rays. So X-rays can be shined into our solid there, and based on the way that the X-ray is diffracted into a screen like this, then you can figure out what is the connection between the different atoms inside that solid, how the molecules are shaped. And this is the way, by the way, that we found how the DNA structure was, by looking at the X-ray diffracted into the DNA. And that's another beautiful story that we have to talk one of these days. So how do we study that? It is based on the way that the diffraction of the X-rays is happening. This is a very nice drawing here, where we can see how the rays will behave as they are diffracted inside the solid, and the difference in the pattern, the distance that this ray traveled here, the path difference between these rays, is going to give us a sense of how far these atoms are, what is the lattice structure of the solid, and so on. So we will be talking about a formula that relates here the difference in the path here, the angle of refraction here of these rays into the distance between the atoms and so on. The important thing here to realize is that there is going to be a way of talking about what we define as the unit cell. These unit cells have different characteristics. One is that they are three-dimensional. That means that they are going to be in space, as we can see here. This is one difficulty that we have as we make these drawings. But the other thing we have to be aware is that the shape of the unit here will depend on how the atoms are arranged. So let's think about these four atoms that are making a solid here, and let us ask the questions. Well, this unit cell here that I have as a model of the solid, very simple model, just a cube. How is this going to be related to the atoms that I have here? And one question is, well, how many atoms are making this cell? Well, when I look over here, if I look in a three-dimensional figure here, I see that each atom really belongs to 8 different cubes. So instead of having one atom belonging to this center cube, I have this atom belonging to 8 different cubes. So in fact, for a unit cell, in this case, I have 8 corners, but I have one atom of each atom belonging to that corner. So the total number of atoms belonging to that unit cell is 1. So this kind of cell will have one atom associated to this thing. And this is very important because if you want to know what the density is, the density, of course, is mass over volume. So if I know what the volume is just by looking at the distance here, the volume is going to be equal to distance cubed. And then if I know the mass by knowing what the molecular mass of these atoms is, so I can always calculate what is the density. Or if I want to go in the opposite direction, if I know what the density is, I can always find what the volume is if I know what the molar mass is of the atom, and then with the volume I can know what the distance is here. So this is how we are going to be using these unit cells in order to distinguish what the density is, or what the density molar mass relationship is. So if I have a simple cube, I have only one atom in the unit cell. The coordination number is 6 in this case, and the side of the cube is equal to 2r, as we saw here. The distance here, if the radius of the atom here, r, is this one here, then the distance of the cube is going to be, in this case, only 2r. So when we look at this, we can make a relationship between the radius, the side of the unit cell, and of course, if we know the density, we can calculate the molar mass and vice versa. If I have something like this that we call a body-centered cube, then I have 2 atoms that belong to that. And I'm going to let you figure out why do I say that I have 2 unit cells. And if I have a face-centered cube, like this one here, then I have 4 atoms. And again, I'm going to let you figure out why do I say that we have 4. So I will see you in class. I hope you have a wonderful weekend.